Hello everybody, welcome to the World of Control channel. I'm Mohammed, and in this video I want to model a planar DOF robotic arm, and I want to show you how to model such these systems and simulate them in the Simulink of MATLAB. As you can see, in this PDF, we have the schematic of our system, the 2 degree of freedom robotic arm. It is a planar manipulator. We have the first link here with the A1 length and the second link with A2 length. We have theta 1 and theta 2 as the 2 degrees of freedom of this system. And also we have M1 and M2 as the mass of each link for this system. In this model, you can see the coordinate systems that we attached to our joints and our end effector here. So let's begin to extract the dynamic equations of this model. First of all, we need to write the BH parameters table for this system. Hartenberg parameters actually. We can see that we have 2 links, and A1 alpha A of I and alpha of I and DI and theta I are the 4 parameters that we have to extract for our system and for each degree of freedom of our system. You can see that we extracted Hartenberg parameters in this table, and we have all of the parameters here shown in this table. After that, we need to write the transformation matrices with respect to our Hartenberg parameters table. By considering the Hartenberg parameters, we can write our transformation matrices like these matrices here, and this is actually our forward kinematics of our system. Okay, after that, we need to write the kinetic energy. We can write the kinetic energy of our system like this equation here, and after that our potential energy that you can see in this slide here, PE is equal to some terms here. And after that, by having the kinetic energy and potential energy here, we can write the Lagrangian of our system, that is the kinetic energy minus the potential energy, that is called Lagrangian. And with respect to this Lagrangian equation here, we can extract our equations with Lagrange method here. We know that the Lagrange equation is like this equation here, that the Q here is our generalized forces, and we need to take some derivatives here and extract our equations. And by taking derivatives and putting the equations in this, putting the actually terms in this equation, we can extract the equations like this. We have 2 degree of freedom, so we will have 2 equations for each degree of freedom. And by considering Q as a vector of theta 1 and theta 2 as generalized parameters for degrees of freedom, we can write our B of Q, C of Q, and G of Q like these matrices here, B of Q is actually our inertia matrix, and C is our damping matrix, and G is our gravity matrix. So let's simulate these equations in our Simulink. So I will open up a Simulink blank model here. Okay, let's wait until the blank model is opened. In this video, I just want to simulate the dynamics of our system, and in the next videos, I'm going to design different controllers for this model. So make sure that you subscribe this channel. First, I want to add a MATLAB function to code our dynamics. In that, I will rename it as dynamics, and I'm going to go in it and let's code this equations here. We know that our output is Q double dot, and our inputs, we have parameters and Q and Q dot, and actually tau as an input. We can see that tau 1 is tau 1 and tau 2 is tau 2, and theta 1 is Q1 and theta 2 is Q2, and also theta dot 1 is Q dot 1 and theta dot 2 is Q dot 2. So we can extract the parameters, also our constant parameters m1 as the mass of the first link, parameters of 1, m2 is parameters of 2, L1 is parameters 3, L2 is parameters 4, and that's it. Oh, we have G as the gravitational acceleration as parameters 5. And after that, we have B as a matrix, 2 by 2 matrix. Okay, the first one is we have 3 terms in it. We have L1 powered by 2, M1 plus M2. The second term is M2 multiple L2 powered by 2, and the third one is 2 M2 L1 L2 cosine of theta 2. M2 L2 square minus M2 L1 L2 cosine of theta 2. The third one is, we have two terms in it. The first term is M2 multiple L2 powered by 2, and the second term is M2 multiple by L1 L2 cosine of theta 2, and the last one is M2 times L2. This is our initial matrix. C is equal to a vector minus M2 L1 L2 sine of something multiple to sine of theta 2, actually that's theta 2 multiple by two terms, 2 times theta dot 1 times theta dot 2 plus theta dot 2 squared. And the second one is minus M2 L1 L2 sine of something multiple by theta dot 1 times theta dot 2 sine of theta 2. And our gravity vector is okay, we have two terms, minus something M1 plus M2 L1 G sine of theta 1 minus M2 times L2 times G times sine of theta 1 plus theta 2, and the second term is minus M2 times L2 times G times sine of theta 1 plus theta 2. Now we have our Q double dot is equal to B backslash something. Backslash means B inverse times our actually right terms. We have our Q, so we have to make our Q here. Q is a vector that is, the first one is tau 1, and the second one is tau 1 minus tau 2. So here we can write Q minus something and minus G. The first one is minus C times Q dot. Q dot is here our Q dot that we imported in our function here. Now Q double dot is ready. Let's save this as dynamics. And now our dynamics function is ready. Let's import some constant blocks to make our parameters L1, L2, and G. G is 9.81, and for now, for example, both of the arm lengths are 0.1 meters, and we have 1 kilogram for each mass of our links. So we add a max here, we change it to 5 and resize it, and we connect the parameters signals here and add to our parameters. Q double dot, we need an integrator to integrate from our Q double dot. This is Q dot. We have our Q dot Q here. And now we feed back our Q dot and Q dot, Q and Q dot here. And for now, I want to add an input. For example, 0 and 0 for now. And we can now show our signals. I want to add a demox here to extract both theta 1 and theta 2 here. Also, we can extract theta dot and theta dot 1 and theta dot 2, but I want to just show and demonstrate just the angles of our robotic arm. Let's change some appearance. Settings here. Okay, that's enough. Let's change this. For initial conditions, for example, the first angle starts at from P minus pi minus by 2, and the second one is 0. Okay, now we can simulate our model for example, 10 seconds. We have a type error, I think, tau 1. Okay, let's modify this one, tau 1. Okay, let's again run the simulation. Another error here, we have we need to change this actually again, 0 and 0, and again run this. Theta dot, we have another type error again, theta dot let's see, line 29, theta 2, theta dot 1, theta dot 1, theta 2. Oh, this is a type error here, theta dot 1. Okay, let's run it again. Another error, we have C times Q dot, C times Q dot. We need to dot we need to add a dot there. And now we run the simulation and we can see that nothing changes. So let's change this to p divided by 6. I think something is wrong again because it doesn't change. Let's see why. PQ minus CQ dot. CQ dot, the first term has to multiple to Q dot 1 and the second one has to multiple to Q dot 2. So let us change the inputs. For example, we have 1 as the first one. We have to see something different. Yes, something is different, but I need to see the dynamics of our system without any inputs. So let's modify this to see how it works. Let's change some parameters here. For example, second one is 10 kilograms. Something is wrong here, I think, because maybe we have a problem in our equations here. Okay, let's add a sine wave here. Signal generator and both of them as a signal generator here. No, you cannot do this. You have to add a mux and change the inputs as shown here. For example, change the amplitude of this one. Let's see how it works. Yes, you can see that the first term is our theta term and the second one is our theta dot. This is our theta 1 and the second one is theta 2. In the next video, I'm going to design different controllers for this system. Make sure that you subscribe this channel because I'm going to make a lot of videos about designing different controllers and also modeling dynamic systems. Thank you very much.